Deep within this remote mountain facility, engineers are constructing the most advanced, hyper-realistic humanoid robots in history. The manufacturing process begins with a digital blueprint designed to mimic the exact proportions of human anatomy.
Technicians use high-resolution laser scanners to capture the minute surface details of a living human donor model.
These data points are converted into a three-dimensional mesh that serves as the foundation for the chassis.
Industrial 3D printers fuse titanium powder into lightweight, durable skeletal structures that replicate human bone density patterns.
A robotic arm retrieves the newly formed titanium pelvis.
Precision milling machines carve aircraft-grade aluminum into the complex rotational joints that will allow for fluid movement.
Technicians install high-grade ceramic ball bearings into the hip sockets to reduce friction during repeated mechanical locomotion. Miniature hydraulic pistons are inserted into the thigh chassis to simulate the contraction of major muscle groups. The assembled leg unit undergoes rigorous stress testing to ensure the actuators can withstand rapid, repetitive motion. Individual metal vertebrae are linked together with flexible polymer discs to create a supportive yet bendable spine. Primary power and data cables are threaded through the spinal column to protect them from external damage. The carbon fiber rib cage is bolted to the spine to house and protect the sensitive internal battery. A high-capacity lithium battery pack is lowered into the chest cavity to serve as the power source. Power cables are soldered to the main distribution board, which regulates voltage across the entire robotic system. Liquid cooling pipes are routed around the battery and motors to dissipate the heat generated during operation. Robotic arms are attached to the shoulder yoke using harmonic drive gears that offer zero backlash precision movement. Micro actuators inside the forearm pull on high-strength cabling tendons to curl the mechanical fingers into a fist.
Tactile pressure sensors are adhered to the fingertips, allowing the robot to feel the texture of objects.
The completed skeletal frame now stands fully assembled, ready to receive the complex network of electronic nerves.
Technicians carefully weave thousands of color-coded wires through the frame to connect every sensor to the brain. A vestibular sensor module is installed in the pelvis to maintain perfect balance and orientation during movement.
High-definition camera modules are secured into the orbital sockets to function as the primary visual input system.
Binaural microphones are embedded in the auditory canals to allow the robot to localize sound in space.
The central processing unit is slid into a shielded cranial casing to protect the neural network hardware.
Data cables connect the optical sensors directly to the processor, enabling real-time image recognition and depth perception. The cranial unit is mounted to the cervical spine mechanism, allowing for realistic head tilting and rotation.
A specialized vocal synthesis speaker is installed in the throat chassis to project the synthesized human voice.
Diagnostic software runs a complete system check, verifying that all electronic pathways are functioning within nominal parameters. The skeletal frame takes its first automated steps on a treadmill to calibrate the walking algorithm software. In the chemical laboratory, specialists mix medical-grade silicone with pigments to create a realistic synthetic skin base.
Microscopic red fibers are added to the mixture to simulate the appearance of capillaries beneath the skin.
The liquid silicone is poured into negative molds taken from human donors to replicate natural skin texture.
The molds are placed in a vacuum chamber to remove air bubbles that would ruin the translucent finish.
Once cured, the flexible silicone skin is carefully peeled from the mold, revealing a seamless human replica. Artisans trim away the excess material from the seams using scalps to ensure a perfect fit later. Painters airbrush faint blue veins on the underside of the skin to create a sense of biological depth.
Surface details like freckles, moles, and age spots are hand-painted to break up the artificial uniformity. The face requires the most complex molding process to capture the delicate geometry of the nose and ears. The facial skin is removed as a single piece, designed to stretch over the mechanical skull's robotic actuators.
A matting agent is sprayed over the face to eliminate the unnatural shine inherent to raw silicone material.
Specialists insert individual strands of human hair into the brow ridge using a fine needle for realism. Eyelashes are implanted at specific angles to ensure they do not interfere with the blinking mechanism's movement. Ocular technicians hand-paint the iris pattern onto acrylic spheres to match the depth of a human eye. The artificial cornea is polished to a glass-like finish to reflect light exactly as a biological eye would.
The finished eyes are snapped into the robotic sockets, immediately giving the machine a startlingly lifelike appearance.
Dental acrylics are used to cast a perfect set of teeth and gums to fill the mouth cavity.
The dentures and a soft silicone tongue are installed, essential for forming correct shapes during speech simulation.
Technicians carefully stretch the silicone skin sleeves over the metal legs, hiding the complex machinery underneath forever.
The torso skin is secured, and the seams are fused together with liquid silicone to make them invisible.
The hand skin is glued to the fingertips to ensure the silicone moves in unison with the metal.
The face mask is draped over the skull and attached to dozens of small anchor points on actuators.
Micro hooks connect the corners of the mouth to the servo motors that will control smiling and speaking. The eyelids are connected to the blink mechanism, requiring precise tension to ensure the eyes close fully.
With the skin attached, the hair team begins the long process of punching thousands of scalp hairs.
Stylists cut and shape the hair to the client's specifications, completing the illusion of a human head.
The robot is dressed in standard clothing to protect the silicone body and further blend into society.
The fully assembled unit is powered on, and the eyes immediately focus on the nearest technician's face.
It performs a self-calibration sequence, flexing its fingers and rotating its wrists to verify skin elasticity limits.
Engineers run an expression cycle, testing the range of emotion from a subtle smile to extreme shock.
The random blink algorithm is activated, preventing the unblinking stare that often reveals a robot's artificial nature. Lip sync software matches the jaw and mouth movements perfectly to the phonemes of the synthesized speech output. The unit is disconnected from the safety tether and allowed to walk freely across the laboratory floor. Fine motor skills are tested by having the robot grasp a fragile egg without cracking the shell. Conversely, the actuators are tested for raw power, effortlessly lifting heavy payloads while maintaining a human posture.
In the social interaction lab, the AI is trained to maintain eye contact and nod at appropriate intervals. The onboard camera analyzes the human interlocutor's facial micro-expressions to adjust its own emotional response in real time.
LiDAR sensors hidden in the chest allow the robot to navigate crowded environments without colliding with obstacles.
Environmental chambers test the silicone skin's stability when exposed to extreme heat or freezing cold temperatures.
Joints undergo millions of cycles in fatigue testing to guarantee the robot can operate for years without maintenance.
Before leaving the factory, the latest artificial intelligence model is uploaded to the robot's local storage drive.
Quality control inspectors examine every square inch of the synthetic skin for tears, bubbles, or painting errors. The face is gently cleaned to remove any dust or oils accumulated during the long assembly process. A unique serial number is laser etched onto a hidden metal plate inside the wrist for identification purposes.
To save space during shipping, the robot is commanded to enter a compact crouching or seated powered-down mode. Layers of anti-static foam are wrapped around the body to prevent damage to the electronics or skin. The unit is lowered into a reinforced, shock-proof flight case designed to withstand rough handling during transport. The charging docking station and technical maintenance manuals are packed securely alongside the primary humanoid robot unit. Heavy-duty latches seal the case, creating an airtight environment that protects the delicate components from humidity changes.
Warning labels indicate the presence of high-voltage lithium batteries and the fragility of the contents inside.
Forklifts transport the crates to the outgoing loading dock, where they join dozens of other completed units.
Secure transport trucks with air ride suspension systems are used to deliver the robots to their final destinations.
The convoy leaves the secure manufacturing facility, transporting the artificial laborers to clients around the globe.
Upon arrival, the case is rolled into the client's facility, ready for the initial setup and activation. Technicians unlock the case and reveal the sleeping machine, which looks indistinguishable from a resting human being.
A wake-up command is sent, and the robot unfolds itself, standing up to greet its new owners.
The handshake is firm yet gentle, the silicone skin warm to the touch due to internal heating.
These units are increasingly deployed in hospitality roles, serving as receptionists that never tire or require breaks.
In the service industry, they navigate busy restaurants with trays of food, calculating optimal paths to tables. Their strength and gentle touch make them ideal for elder care, assisting patients with mobility and daily tasks.
Others are sent to hazardous environments where they perform dangerous maintenance tasks, without risking human life or health.
As AI advances, the line between the programmed response and genuine understanding becomes increasingly difficult to distinguish.